Hey there guys, welcome back to another video. It's almost the end of the school year, but there's still one last barrier to jump over, and that's this AP Physics 1 exam. And so instead of making a super long and lengthy review video, I decided to do something a little bit different and put together 10 tactical hacks so that way you can apply it per question and hopefully decrease the amount of time it takes to do each question, and then hopefully therefore increase your overall score. Now, this is something that I haven't seen done before, and this is really something that's personal to me and my experience with teaching this and helping people get fives via paid programs. But again, in this video, I'm going to give it all away for free in the shortest amount of time possible. And so all I ask is that if this does help you, please leave a like, please subscribe, and also check out nerdnotes.com. Tons of free resources for you to use as you approach that AP exam date. All right, without further ado, let's move on to hack number 1. This hack says that every question can be solved in under 90 seconds or less. If it's taking you longer, you're not reasoning like College Board wants you to. Now, this hack is sort of the core fundamental thesis of like improving your score. Whenever I help people improve for their scores, I always track their time per question. And if it's taking them longer than 90 seconds, I automatically assume that it's not that they don't know how to do it, it's more like they're not doing it in the right format or in the right way or thinking in the right way. And so again, this is like kind of like the core thesis behind the rest of the hack. So everything is going to be optimized towards getting your time per question under 90 seconds. And by the end of this video, you'll find out that you can probably solve most of these questions in under 60 seconds. And so again, it sounds like a dream, but the more we uncover and use these hacks, the more you'll realize it's totally possible. Now, before we do a practice question, let's take a look at hack number 2. So this hack says if you see a long text wall, skip over it. The reason being is because reading takes the longest time out of any part of the question, more than it probably takes to actually solve the question itself. And so if you're just reading, you're killing time essentially. And so to avoid having to read too much, what you want to do is you want to skip to the very last line, and it will tell you exactly what to solve for. College Board does a really, really good job of being consistent with this. And then once you sort of figure out what you're solving for, you have two options here. You can start to derive an equation straight off the bat, or you can maybe go back and read the rest of it with at least intention, which means that at least you kind of have an idea of what they're asking for. So as you read the problem, it will make more sense. Take a look at this problem over here. If I was to read this whole question, it would take me about 20 seconds, given that there's about 70 words in there and I'm reading at the average reading pace. Now, if I get to the very end of the question and I finally realize what they're asking me, and I also realize that I probably didn't really understand what they were saying up here, so I need to go back and read it. And so instead of doing this and spending a total of 40 seconds reading it once and then maybe again, I can simply start from the very end, see what they're asking, and then maybe go back and read with intention. And so what are they asking in this case here? What is the magnitude of the angular momentum of the rod? Cool. Angular momentum of anything is going to be L is equal to I omega. Maybe alternatively, we can use conservation of angular momentum in the case of a collision, which we can see up here just from the diagram. So maybe we can use the initial angular momentum is equal to the final angular momentum. And so just like that, I have something written down on my paper. Now, we're not actually going to solve this question, at least not yet, but I just wanted to show you how skipping to the last line sometimes is a really big time saver. Hack number 3. Every question is hiding an equation or law, even the conceptual ones. Find the equation fast, and you'll stop having to reread the question like it's a riddle. Now, this is the most common mistake I see people make. I see people sort of read the question and just sit there and not do anything. Now, this hack, what it's really saying is that if you can't get an equation down within the first, I would say 20 to 25 seconds, maybe even less, then you're probably not going to get the question right. So what you really want to do is train your brain as you're practicing to recognize some of these common scenarios and what principles/laws/equations they tie into. And the cool thing is that you don't need to sort of get the right equation every time. You just need a starting point. That's it. And once you figure out that starting point, then your brain will just sort of automatically start filling in things for you. All right, so using those 3 hacks that we just talked about, let's try to apply it to this problem here. And before I even solve it, I encourage you to try to use those hacks by yourself. Pause the video, try to use it and solve the problem by yourself in under 90 seconds. And if you can do it, you're following along well. And if you can't, it's okay. It's going to take some practice. And so pause the video, try it out, and now let's do it together. Okay, so reading the last sentence, which block, if either, has a greater mass? Okay, so we're looking for essentially mass. And looking at the diagram here, we can see that there's some sort of collision going on. So when I think collisions, I think that momentum is conserved, because in any collision, momentum is conserved. So Pi is equal to Pf. Now I'm going to go ahead and apply it. I'm going to say ma times the velocity of A, which just happens to be v naught, as they labeled, is equal to The final momentum. Now, after the blocks collides, I don't really know what happens. The diagram doesn't tell me that. So what I can now do is I can go back and quickly skim through the rest of the question with intent. So 2 things I'm looking for. 1, what kind of collision is it? And 2, what happens to the velocities? Okay, so it says block A is moving with the initial velocity of v naught. Okay, we got that. And then it says the 2 blocks collide and stick together. Aha, there's our first piece of information. So stick together means inelastic. So they're going to combine masses, which I can then write as ma plus mb. And as for the velocity, as we keep reading, it says that they move off with the velocity of v naught over 3. So a third of the initial speed, essentially. Now, once you get to this point, a lot of people make the mistake of starting to reason. They try to start looking at, hey, okay, which one would be bigger based off maybe the equation? And honestly, sometimes that is a good way to do it. But in other cases, when you have kind of like an unsimplified equation, the best thing to do is start to simplify it. So the first thing I can do actually is just cancel out the v naught on both sides. So that v initial will cancel out. Next thing I can do is I can multiply by 3 on both sides. So it's going to be 3ma is equal to ma plus mb. And then what I can do is I can go ahead and subtract ma from both sides. So we can see that 2ma is equal to mb. Okay, cool. Now we have sort of a ratio. And that ratio tells us that the mass of block B is 2 times the mass of block A. So which one is the bigger block? Obviously, mass B has to be the bigger block. So B is your answer, and you can move on. So again, just to recap, look at how much reasoning I had to do. Actually, very little, right? I didn't have to sit down there and ponder the question and think about it in 10 different ways. I simply just applied conservation of momentum, which I initially saw from the fact that it's a collision. And then I just derived. That's all I did. Hack number 4, derive or die trying. So again, this ties very well into what we were just doing, but specifically I'm talking about the questions where you see numbers. A lot of the times what I see is that whenever you see numbers, people get too excited and they start plugging it into equations and calculating values. The reason you don't want to do this is because things often tend to cancel each other out. And so you're just going to be wasting time punching in numbers into the calculator. This is not a math test. This is a derivation test, if anything. So that basically means you need to trust the algebra more than you trust your TI-84. This is a core rule. So to test this derivation hack out, go ahead and pause the video and try to apply it to this problem here. Alright, now that you tried it, let's go ahead and do it together. This problem looks very lengthy, but I can see that I have a diagram. And so again, one of the hacks is that if I do have a diagram, let's just use that to interpret what's going on instead of reading. So we can see that block A is sliding down a length of 3.6, and it's going to collide, it looks like, with block B. So as soon as I see collisions and that it's sliding down, I immediately think, okay, I'm going to be using some sort of conservation of momentum and maybe some sort of kinematics or energy. Okay, let's go ahead and read the question now. The speed of the blocks after the collision is most nearly. Okay, so they're asking for me for the speed of the blocks. And it looks like they're maybe moving together, which suggests an inelastic collision. And just to verify, we can again skim through the question here and look for that key word. So it says it right here. Block A hits and sticks, which verifies that it is indeed an inelastic collision. So that being said, let's go ahead and start deriving. So Pi is equal to Pf. And so mass A times velocity A is equal to mass A plus mass B times velocity final that we're trying to look for. Now at this point, what you want to do is you want to ask yourself, okay, what are we missing? Well, we have mass A and we have mass B, and again, we can quickly skim through the equation and look for those kgs. And so we see that we have 2 masses, and so therefore all we're missing is VA. As soon as you figure out you're missing VA, just go ahead and derive an equation for that. Well, how do we derive an equation for VA? Well, we can simply just use conservation of energy or maybe kinematics. And so actually, one of my rules is that if you can use kinematics, you can probably also use energy, and energy is almost always easier to do than kinematics is. And so what I can do here is I can start deriving an equation for velocity, and I can say something like, okay, well, energy is conserved, so my initial energy should be equal to my final amount of energy, EI is equal to EF, and my initial energy starts with potential, so mgh, and that's equal to 1/2 mv squared. The masses cancel out, and if I solve for velocity, I get root 2gh. And now I can go ahead and just plug this velocity into that, and I'm going to get ma times root 2gh is equal to the total mass of ma plus mb. And at this point, we can just go ahead and plug in numbers now. And so to do this really quickly, what I can do is I can plug in mass of A. Now, height is super easy to find. What you'll notice, College Board will always give you very nice angles to work with. They'll always give you 30, 0, 60, 90. And sometimes they'll give you something like 37 or 53, which actually is a 3, 4, 5 triangle, which you can then reference in your equation sheet that they'll give you. So it's a very, very simple hack there as well. And so in this case, if we want to find the height, all we have to do is do 3.6 sine of 30, because that's the opposite side. And so sine of 30 is half, and half of 3.6 is 1.8. Bringing that 1.8 into this equation here, 1.8 times gravity, which is 10, is 18. 18 times 2 is 36. The square root of 36 is just 6. So as you can see, this is why my other rule from before was that this is not a math test. This is a derivation test. The math is super, super simple, as is the case in this problem. And the total mass here is going to be MA plus MB. So let's finish that off. That's going to be 5 VF. And as you can see, the rest of the math is pretty simple. It's just going to be 12 divided by 5. And so 12 over 5 corresponds to 2.4, and you're pretty much done. Now again, this way might seem like it takes longer, but I promise you that over time, as you get more and more practice with these questions, this way becomes substantially faster. Okay, moving on to the next question here. Now this one I'm not going to do fully, just for the sake of time, but what I want you to do is pause the video and apply the same principles that we did. Alright, now let's go ahead and try to solve this together. Notice how we don't have a diagram, so we're kind of forced to read the whole problem. But again, let's try to use our hack of actually skipping to the part of the question that tells us what to solve for. In this case, I see the question mark right here, so I'm going to read that sentence. What percentage of the initial mechanical energy of the apple or its system is dissipated due to air resistance? Cool, so we're looking for a percentage, which is basically just a fraction of the amount of energy that's lost. And so if I want to find that, I can just simply do the amount of energy that's lost divided by my initial amount of energy and multiply that by 100 to get a percentage. But let's leave this as a fraction for right now. Let's expand this out a little bit. The amount of energy lost is simply the difference between how much you start with, so EI, minus how much you end with. And of course, this is all going to be divided by EI. And if you want, you can simplify this just a little bit more to 1 minus EF over EI. Okay, now at this point, you kind of have to stop and ask yourself, what is the final energy and what is the initial energy? And so now it's totally fair to go back to the question and reread it with intent. And so now we're looking for two types of things, the final energy and the initial energy. And so let's start reading. It says an apple is released from rest 500 meters above the ground. Cool. Release from rest means that there's no kinetic energy, but there is potential energy due to gravity. So it starts with 100% of potential energy. Let's keep reading. It says due to the combined forces of the air, resistance, and gravity, it has a speed of 40 meters per second when it reaches the ground. So by the time it reaches the ground, it's going to gain some kinetic energy. And so the final amount of energy is kinetic. And so let's go ahead and plug that into our equation. So I'm going to bring that equation down here. 1 minus final energy, which we said was kinetic, so 1/2 mv squared, divided by the initial amount of energy, which was potential, like we said, so mgh. Notice how those masses cancel out. We simplify just a little bit more, and our final equation is going to be v squared over 2gh. All right, from here you can plug in all the given numbers into your calculator, or if you're fast enough, you can even do it in your head, and then get a final answer of 84%. So just to recap, look at how much working we did. Look at how much reasoning we had to do. We didn't just sit here with our hands in our head. We actually put down an equation within the first few seconds. We expanded out that equation, and we looked meaningfully for things that we actually needed instead of aimlessly reading through the entire thing. So if you can replicate these steps and the hacks that we're doing across all these problems, you will get faster at problem solving as you do more and more practice. Now let's move on to the fifth hack. Alright, so this hack is actually something that I've already touched upon in earlier problems, and it basically says that if a diagram is included, try to understand it first, so that way you can avoid reading the question, and then you can just skip to the last part of the sentence. Because oftentimes, if you are given a diagram, the wording in the question is just kind of a regurgitation of what's going on in the diagram. So they're just trying to explain the diagram to you in words, and this is a very common AP tactic to kind of kill your time. And so as you spend all that time reading it, again, you will end up with less time to solve the problem. And so just skip the reading, look at the diagram, try to understand it, read the last sentence, and then if you really do need to, you can always go back and read it, okay? So this is a hack that honestly saves so much time. And so let's take a look at a problem where we can apply this. And it's actually going to be the same problem that we were doing earlier, but now we're actually going to solve it and apply everything that we've learned so far. All right, so go ahead and pause the video and try it out by yourself. All right, now let's try it together. Straight off the bat, I see a diagram, which means that let me try to interpret that first before I read the question. And so looking at just the diagram, I can see that there's a ball or something that's colliding with this rod that sets the rod into rotational motion, and it looks like that ball or that object rebounds backwards. So immediately in my head, I'm thinking collisions. And when I think collisions, I think conservation of momentum. Specifically in this case, I'm thinking conservation of angular momentum because that rod is rotating. And so I'm going to say Li is equal to Lf. All right, cool. So that's as far as I can probably go with just interpreting the diagram. Also, this P looks like it might stand for momentum initial and momentum final, but I can't tell for sure. So let me go ahead and actually read the last bit of the question and see what it's asking me for. So it's asking me, what is the magnitude of the angular momentum of the rod immediately after the collision? So again, they're asking me for angular momentum. Well, how do I find angular momentum of the rod in this case? Well, all I need to do is do L is equal to I times omega. So as long as I have the moment of inertia of the rod, and as long as I have the angular speed of the rod, I can totally find the angular momentum of the rod. And so keep in mind that I'm missing these key pieces, so I need to skim through the rest of my question to find them. And so again, I'm reading with intent. So I'm going to go and skim through the question, looking for maybe somewhere where it says I. And as I can see there, it doesn't really say anything about I or omega. And so in other words, this kind of method, this kind of becomes invalidated. And that's totally fine. You're going to run into the situations where the first way you try doesn't work. And so what do you do from here? Well, you go back to basics. We know that this doesn't work, so let's just go back to conservation of momentum and try to derive a formula from that. We know that the initial momentum of the ball is simply LBI. And we know that after it collides, the ball is going to be moving in the opposite direction, and the rod's going to have some angular momentum as well. So the rod is going to have LR, let's call that angular momentum of the rod, and then we're going to do plus negative L of the ball final. And so from here I can clearly see that I can solve for the angular momentum of the rod simply by adding the final angular momentum of the ball to both sides. So let's go and try that out. So it's going to be LBI plus LBF is equal to the angular momentum of the rod. All right, cool, we're getting somewhere, but it doesn't quite match up with any of our answer choices here, so we got to keep deriving. And so what is the angular momentum of the ball? So that's going to be simply the linear momentum of the ball, which is pi, and we can verify that that is indeed linear momentum by quickly skimming through the problem and trying to find that part. So it says right here, pi is the linear momentum. Okay, so that indeed is linear momentum, and linear momentum multiplied by the lever arm is going to be what we call angular momentum. So in other words, pi times d, and then plus the final angular momentum, and guess what? That's going to be going backwards, but we already took the sign into account, so we don't need to worry about that. And so we can basically just say pi, or pf, excuse me, times the distance is going to be my final angular momentum, so pf times d, and that's equal to lr. We can also factor out the d if we wanted, and at that point you can probably just do it in your head and see that that probably matches up closest to this equation right here. All right, let's move on to hack number 6. This hack says that if you're given graphs, this is pretty much a freebie question for you. You want to interpret the graph before anything else. It's usually trying to spoil the answer. And so here's what I mean by that. All right, so for this question, you might be tempted to sort of jump in and start reading, or according to one of our hacks, maybe just reading the last part of the question. But there's one more hack that you might want to try applying before you do that. And that's actually figuring out what the graph is trying to tell you. And by that, what I really mean is find the slope of the line, or find the area under the curve, and specifically tell me what that means. And so if you're finding the slope of the line, in this case, that's going to be force divided by time. And what's force divided by time? Maybe you can take a look at your equation sheet, in which you'll quickly realize that it's nothing that you know. So force divided by time doesn't give us an actual, usable number. However, if you look at the area under the curve, how do you calculate area? It's going to be base times the height, right? So that area is going to be force times time, which sounds a little bit more familiar, and that's going to be impulse. And so in this graph, College Board is basically screaming at you and telling you that, hey, I'm giving you impulse. So whatever you do in the question, please use impulse. And so using our other hacks, let's go down to the very last bit of the question and read it. Which of the following is the best estimate of the net change in speed of the spacecraft from t0 to t equals 4. So what are we really looking for? We're looking for change in speed. So we're looking for delta v. And so is there any equation that maybe uses impulse and delta v? Well, heck yeah. The equation for impulse is literally f times t, or the other equation is m delta v. And that's as simple as that. Now that we know we can calculate our impulse from just looking at the area, then we can simply divide by mass on both sides to get the change in speed. and you're done. So let's go and do that. What's the area of this triangle here? Well, the area of this triangle is going to be essentially the height, which is 1,000, times the base, which is 2, so 2,000, but it's a triangle, so we need to divide by half. So we have an area, net area of 1,000 here. And then looking at the next segment here from 2 to 3, it's a flat line, so there's no area there. And looking from 3 to 4, it looks like we have a base of 1 and a height of negative 500. So we have a total area of negative 500. Okay, cool. So what's my net area under the curve? Well, it's going to be 100 plus negative 500, which gives me a net area of 500. And so my impulse is 500. And to find delta V, I just need to divide by mass on both sides. Again, this is the part of the question where you probably don't know mass because we haven't read the question, so we might want to skim through it to look for that mass. So skimming through it, we see that it's right here, 4,000, and we can just plug that in. So instead of mass, we can replace that with 4,000. 2 of the zeros cancel out. We get 5 over 40. 5 over 40 is 1/8. And 1/8 is about 0.125, which matches closely to 0.1, which is option B. Let's move on to the next question here. All right, so this is another graphing question, and I actually want you to pause the video for this one and try it out yourself. See if you can apply the same hacks that we just did to solve this problem. All right, now that you tried it, let's go and do it together. So because we're given a graph, we want to interpret what that graph is trying to tell us. In this case, we can try two things. We can try the slope or the area. Let's try the slope first. The slope is going to tell us force divided by distance, and according to my knowledge, that doesn't really tell me anything useful. So I'm going to try to see what the area is trying to tell me. The area is going to be the force times the base, which is the position, so force times distance essentially, and that's going to be work energy, right? So immediately, straight off the bat, we know that the graph is trying to tell us, hey, whatever you do in the problem, try to use work energy. All right, now let's read the last part of the question. What is the mass of the object? And so again, from that one sentence, we can't really tell too much, but they're asking for mass, right? And so maybe we can start to jog our memory as to how work and mass relates. And in this case, there's several ways it relates. And I'm thinking that we can simply just use the work energy theorem, right? Work is equal to delta KE. And in this case, the work is the area of the curve. And delta KE will just be 1/2 m v final squared minus v initial squared. And looking at this, if I want to solve for mass, I would need initial speed and final speed. So now I have to kind of go back through the question and look for those two variables, but at least now I'm reading with intent. So let's kind of skim through them and let's see if I can find some speeds here, and I find it right here, right? So it acquires a speed of 3 meters per second, and so that probably implies that it's final speed. And backtracking a little bit, I see that it also starts from rest. So v initial is 0, and final speed is 3. And so now we can go ahead and simplify the equation a little bit and plug in the final speed as well, so we can get 1/2 m, 3 squared is 9. Okay, and again, we're looking for mass, so the last thing we need is just simply the work, which is the area under the curve, and the area under the curve is simply going to be 0.09, so 0.09, which we can actually just write as 9 over 100, times the height, which in this case is 3, and then times half because it's the area of a triangle. And that's going to be equal to the right-hand side of the equation, which is still 1/2 m times 9. Okay, simplifying this out a little bit, we see that 9 and 9 cancels out. We see that half and half cancels out. We're left with m is equal to 0.03. And we're done. So as simple as that. And which answer corresponds to that? That's going to be B, and we can just move on. All right, so hopefully you're seeing how these hacks are super helpful. It helps me to think less and do more, essentially. Let's move on to hack number 7. This hack says, do not just use the first formula that fits. Instead, write down all versions of the base equation, especially for work energy and impulse momentum. Oftentimes, some of these MCQs, they just love testing your ability to choose the right variant of the equation. So let's take a look at an example here. So looking at this problem, we can see immediately that there's no graph, there's no diagram, so we really have no choice but to read the whole problem. But before we do that, let's actually use one of the hacks that says to read only the last bit first. So let's do that. What is the change in angular momentum of the wheel? So just from the statement alone, we can maybe write down delta L. That is the change in angular momentum. And delta L we can maybe write down as L final minus L initial. And we can even maybe write down another variant that says I times delta omega. And maybe we can write down one more variant that says torque times time. And so these are all acceptable variants, and you can really put so many more, but you don't want to go overboard. And so the whole point of writing out these variants as I've done here, is because when you go back and eventually read the problem again, you are trying to essentially look for those variables within those variants. So, you want to look for LF and LI. In other problems, they're going to give you I and delta omega. In some problems, they'll give you torque and time. And so you want to keep your eyes peeled for those variables. And the only way you can is if you have all the variants written out. So reading through this question, let's kind of skim through it. We see the wheel has a rotational inertia of 2. So again, we have I. There's I there. So we might be using this variant here. And then it says, at the instant the wheel has a counterclockwise angular velocity. Okay, cool. Looks like we're almost certainly going to be using this variant here, because now they're giving us omega. And then it says it has an average clockwise torque is 5 newtons. Okay, cool. Maybe we can use this variant then. And then it continues for 4 seconds. Well, we can just stop right there, right? Because guess what? They gave us torque and they gave us time. And that's one of our variants that we can use to solve the problem. And so delta L is simply going to be 5 times 4. Which is 20, and you're done. So there you go. It's genuinely as simple as that. And a lot of people, they spend too much time maybe on a different variant, and they try to calculate maybe the change in speed. So they're looking for initial and final speed. And what ends up happening is that you can probably solve it. College Board usually gives you enough information, but that's just to waste your time. All right, so moving on to the next hack. This one says, if you see an energy question, just use conservation of energy, especially if you're struggling on the question. If you can't see where they're taking the question, but you know it's an energy question, just use EI is equal to EF. All right, now let's take a look at where we can apply this hack. All right, so once again, pause the video, try it out yourself, and then we'll do it together. All right, now let's try this question together. Straight off the bat, we see a very prominent diagram. I see a runner, or someone that's running, of mass m at speed v towards this either this wall or this rope that's dangling down. And it seems like the same thing's happening over here, but this person is mass 2m, and his rope is much shorter. And so immediately off the bat, I'm trying to think of principles that might apply here. And I'm thinking maybe circular motion if it is a rope and he's swinging. I'm also thinking maybe conservation of energy because his kinetic becomes potential as he swings upwards. And so again, I have a good enough idea in my mind of what I'm looking for. And now I'm just going to go ahead and read the question. So reading the question, going all the way down to the very last bit here, it says, how does the maximum height reached by the two athletes compare? And so I'm almost certain now that this is a rope and that they're swinging. And so in order to find the maximum height, it's probably not going to be using circular motion. That's more like forces. But conservation of energy does deal with heights. And so let's go ahead and do EI is equal to EF, right? Conservation of energy. So as soon as you figure out it's an energy problem, just do conservation of energy. Don't worry too much about how to solve for height. Just put together the conservation of energy statement, which basically says whatever energy that you start with, in this case it's kinetic for both of them. So I'm going to put 1/2 mv squared, is going to transform into the amount of energy that they end with. Now, when you reach maximum height, you're essentially not moving anymore. So the only type of energy that you have remaining is potential, so mgh. Solving this equation for height yields that it only depends on two things here. So v squared over 2g is equal to height. And you can see that the height only depends on velocity and gravity. Now, gravity is the same for both, and the velocity also happens to be the same for both. And so therefore, height's going to be the same for both. All right, so did you see how fast that was? Super, super fast. Didn't have to spend so much time reading the problem, even though it looks like a very, very lengthy problem. Again, College Board is just trying to throw you off and waste your time. And so you want to avoid that as much as possible. So I actually decided to skip hack number 9. It was just taking too long to explain to the level that I wanted to. And I'm just going to skip to hack number 10, which is proportional analysis. And honestly, this is where I want to spend most of my time on. Now, some of you might have heard the term proportional analysis. I honestly kind of just made up this term. Some teachers call it this. Most teachers don't even cover this. And so I wanted to cover it with you just so that way you're aware of how to do these questions. And basically, just to kind of summarize up what this does is that instead of plugging in numbers and solving for a specific number, you're really solving for a relative value. So let me give you a quick example. If I asked you, hey, if you double the angle of a projectile, how much higher is it going to go? Or if you double the velocity of a speeding car, how much further is it going to slide across after slamming its brakes? So those kinds of questions. College Board is very, very they're basically known for doing these kinds of questions, and most people go into the exam not knowing how to solve these. All right, let's try to apply proportional analysis to these two questions. For the time being, I'm just going to blur out the second part so you can focus on the first. Pause the video and try it out. All right, now that you tried it out yourself, let's do it together. I'm not going to time this one here just because I want to teach you how to do it, and then the second question you can go in and time yourself and try to do it in under 90 seconds. So in this question, let's just actually skip to the last part. and read that and see what it's asking for. The surface gravitational field of the planet is most nearly. So they're asking me for the gravitational field. So let's actually just go and write down the formula for that. It's going to be G is equal to capital G times the mass of the planet divided by the radius of the planet squared. All right, cool. So we got something going, but again, this is nowhere near enough to actually help us solve this problem. So let's actually go and read the problem and see what it's actually saying. So a newly discovered planet is found to have a density that's 2/3 that of planet Earth and a radius of 2 times as big as Earth. So whenever you see these kinds of fractions, this is almost a dead giveaway that you need to use proportional analysis. Why? Because what they're basically saying is that, hey, tell me what happens to gravity as you manipulate the density and the radius. And so in order to solve these problems, you need an equation that involves all those variables, and everything else has to be a constant. So let me show you what I mean by that. Looking at this equation, we have gravity and we have the radius, but we don't have density in there. In order to use proportional analysis and in order to find those proportions, we need density. So how do you get density into this equation? Well, you might notice that mass can be easily replaced with a formula that includes density. So let me write down the formula that comes to mind. Density is equal to mass over volume. And so therefore mass is going to be equal to density times volume. And so what I can do is I can replace the mass of the planet with the density of the planet times the volume of the planet. So let's going to write that down. So G is equal to capital G times rho times V all over R squared. So at this point, we can see that we have gravity, we have density, and we have radius, which is exactly what we wanted to be able to do proportional analysis. But at this point, you might want to pause and ask yourself, are all the rest of the terms in the equation constants? And so what I mean by that is capital G a constant? Yeah, absolutely. That's a gravitational constant. Is volume a constant between the two planets? Well, not quite, right? Because as the radius changes, so will the volume. And so to kind of see that relationship, we need to expand out the formula for volume here, or expand out volume to include the formula. And volume, just to put it on the side, is going to be 4/3 pi r cubed. And so let's go and plug that into the equation. So it's going to be G is going to be equal to capital G rho times 4/3 pi r cubed divided by r squared. And one of the simplifications we can make immediately is that the r squared and the r cubed will cancel out, and you just have one r in the numerator now. All right, so now we can effectively conduct proportional analysis, and the easiest way to do it, honestly, to see these relationships, is to move all the variables that you're trying to compare, which in this case is G, rho, and r, to one side. So let me go ahead and do that. It's going to be G divided by rho r is equal to some constants, right? It doesn't matter what those constants are, because all we know is that a constant should stay the same. And so looking at this proportion, essentially, we see that G is directly proportional to rho times r. So in other words, as the denominator increases, the numerator will also increase, and vice versa. If the denominator decreases, the numerator will also decrease. And so looking at this problem specifically, what happens to rho and r? Well, we see that it decreases by 2/3, so rho decreases by 2/3, but radius doubles. And so what's the total net change in the denominator? Well, it's going to be 2 times 2, which is 4 over 3, so that's 4/3. So the denominator increases by 4/3. And like we said, because this is directly proportional to G, if the denominator increases by 4/3, so must the numerator. So gravity, which is usually 10 on Earth, that's going to be increasing by 4/3. Okay, so that's going to go up by 4/3. So which answer choice shows gravity being bigger than 10, specifically 4/3 as big as 10? That's 13, that's D. All right, now what I want you to try to do is the second question. This one is also proportional analysis. And if it's still confusing you, then what I recommend is just doing more of these types of problems until you get the hang of it. I would say just around question 6 or 7 of doing these types of problems, you'll really start to get the hang of it. And to help you out, I've actually categorized a whole bunch of these questions as proportional analysis on my question bank. And so you can quickly just skim through them and pick the ones that you want to do and just quickly solve them. I'm not going to solve this question just for the sake of time. But I believe the answer was A, 2 newtons per kg, if you wanted to check your answer. All right, now moving on here, I wanted to show you how to apply proportional analysis to FRQ questions as well. As I've already mentioned, a College Board loves giving proportional analysis questions, and it's no different in the FRQs than in the MCQs. And usually in the FRQs, they always make you derive an equation, and then they follow it up with proportional analysis. So what I've done here is I've basically scouted out a proportional analysis question, and I've condensed this FRQ. This is from the 2017 exam, but I basically condensed it down so you don't need to read the whole whole entire FRQ, you can just basically solve the whole problem with this much information, and I'm not going to do it with you. And so the setup in this question was basically that a scientist is dropping a steel ball into a container of oil that can thicken as it cools. And they measure how much mechanical energy is lost, and they relate it to the oil stiffness. So obviously, as the oil heats up, it becomes less stiff, and as the oil cools down, it becomes more thick. And so the follow-up question to this was basically, one of the scientists is trying to represent the relationship between oil stiffness and the mechanical energy lost. They write down the equation E lost is equal to CS squared, where C is some constant with appropriate units, and S squared is referring to the stiffness of the liquid, in this case the oil. Some scientists point out that this equation cannot be correct. Give 2 reasons why that equation may not be correct. And so just at first glance, reading through this, your brain might be working in 10 different directions as to how to solve this problem. But in reality, it's just a proportional analysis question. They're asking you really, does the proportion between E lost and S squared, does it make sense? And if you just rearrange it, maybe in this format here, so we can do E lost over S squared is equal to C, we can see that S squared is directly proportional to E lost. And actually that kind of makes sense, right? As the stiffness increases, so should the amount of energy that's being lost. However, what doesn't make sense is that it's squared and that it's going to increase forever. So in other words, as the stiffness increases, the energy lost essentially is uncapped. It can lose energy as long as stiffness continues to increase. And that's theoretically not possible, right? You can only lose as much energy as the system starts off with. And so one of the reasons why it might be incorrect is that the energy loss should eventually taper off. It shouldn't actually increase forever. It shouldn't be parabolic. All right, so again, I'm just applying proportional analysis to solve that question. Let's move on to the second part of the question. Further attempting to model the ball's motion, the scientists write down the following equation. T is equal to Z over S, where Z is a constant, and of course, S refers to the stiffness here. Is this equation plausible? In other words, does it make physical sense? So once again, the same exact type of question as the part before. They're asking you, does it make sense? And the answer is based off the proportions, right? So what I'm going to do is I'm going to move S to the other side. So I'm going to write this as Z is equal to S times T. And so what does this proportion tell me? Well, it tells me that the 2 variables are inversely proportional, which means that as one of these variables goes up, the other must go down to keep Z a constant. So in other words, let's just throw in a random situation here. Let's say the stiffness increases. Should the time decrease? Well, let's think about this. If the stiffness of the oil is increasing, then it's probably going to take longer for the ball to fall through the oil. So time shouldn't decrease, it should actually increase. So that's why, in this case, this equation makes no sense. The time should be directly proportional to the stiffness, not inversely. And so in other words, it's not possible. In your explanation, when you go to explain this, you can literally just point to your proportion and say that, hey, these 2 things should not be inversely proportional. They should be directly proportional because as the stiffness of the oil increases, so should the time. All right, now moving on to the final hack of this review, I've included this as a bonus hack, number 11, and this hack states that the position and velocity of the center of mass remains the same without an external force. This is such a game-changing hack, and I'll show you why in just a second. But let me explain this a little bit more before we move on. This basically says that if nothing is pushing from outside of the system, the motion / the position doesn't change, period. Okay, now let me give you an example of this. Now, again, one of our hacks was to not read the whole question immediately off the bat. We want to look at the diagram. And so looking at the diagram, we see this person on a raft, and we see that he starts at this edge right here. Now, that's all the diagram says, so let's actually read the question. So the question mark is here, so I'm going to start reading from right here. So which of the following best shows the final locations of the raft and the student relative to the marks at the bottom of the pool? So actually, this question doesn't tell me much, actually, so I kind of need to read all of it now. So a student is standing at one end of a raft in a pool with equally spaced marks along the bottom, as shown above. The student and the raft have the same mass. Okay, cool, that's important to know. The student then walks to the opposite end of the raft. Aha, okay, now I figured out what's going on. So the person is actually moving up to the other side of the raft. This is a system where there's no net external forces acting on it, which means if there's no net external forces, there's nothing that can physically change the center of mass. What that means is that wherever the center of mass is currently, before he walks over, it's where it's still going to be after he walks over. So really quickly, to find the center of mass, what do? Well, we take the center of mass of the raft, which is right around here, and we take the center of mass of the person, and then we just average it out. And the center of mass lays right dead in the center between the 2. So just to kind of put it numerically, actually, if we have this as position 0, position 1, and then position 2, kind of like a number line, we know that the center of mass of the current system is going to fall right here. And after he walks over, it should still be in the exact same spot. However, after he walks over, we can maybe draw a different diagram here. After he walks over, we can see that his center of mass, if nothing changed, is actually going to be between 1 and 2. So in other words, if our center of mass started here, but our center of mass is currently being shown as here, we need to move backwards half and another half, so basically a total of 1 unit backwards, so that way my center of mass can align back to where it originally was. What the raft and the whole system essentially needs to move back 1 unit. And so which answer choice corresponds to that? That's going to be C. All right, so now you know what I mean by this hack. So let me just read it one more time, so that way it makes more sense. So the position and the velocity of the center of mass remains the same without any external forces. So as you saw in the previous question, there's no external forces acting on the raft. It was just the person walking across, which is an internal force. And so therefore, the center of mass does not change. It remains in the exact same spot. And by the way, this should probably say motion/position of the center of mass does not change. Now, this motion part here might be confusing you a little bit, and so what I'm going to do is I'm going to solve another question with you, one final question, to show you how it's applied. Now, this question here is pretty lengthy, and so I really don't want to have to read through all of this. So what I'm going to do is start at the very end, like how we've been doing, and read what it says. What is the speed of the center of mass of the system at that instant? Well, that's what I meant by motion, right? The speed, essentially. So we now know that as long as there's no net external forces, the speed/the motion of the center of mass of the system shouldn't change. And so quickly just skimming through this problem here, we have 2 identical blocks, each connected to opposite ends of a compressed spring. The blocks initially slide together with a velocity of 2 meters per second. So that's our first key piece of information right there. The velocity of the center of mass is 2 meters per second because they're moving together. The spring that's in between the blocks is then released by remote control, and some instant later, the left block is moving at 1 meter to the left, 1 meter per second to the left, and the other block is moving to the right. Okay, cool. So again, like we said in our little hack, as long as there's no external forces, which in this case there's none, right? That spring is an internal force. It splits the blocks apart via an internal force. And another way to kind of maybe look at it is that this is a explosion, right? It's a separation of objects in which momentum is conserved. And momentum being conserved simply means that there's no external force according to the equation, right? Conservation of momentum. All I'm trying to say, if I'm trying to say anything at all here, is that because it's moving with 2 meters per second, the center of mass, initially, it's going to continue moving at 2 meters per second even after they split apart. So the final answer is simply just 2. College Board gives the setup so often, and notice how they include so much information, primarily for the purposes of tricking you into actually trying to solve for something. Now, could you possibly solve for something here? Maybe. But there's no point because you know that, again, as long as the center of mass experiences no net external force, it's going to continue moving at the same rate it was, or if it wasn't moving, it's going to stay at the same position as it originally was. Alright guys, that wraps up this review video. Hopefully that was helpful, and if it was, please smash that like button for me. And also, again, if you want to keep practicing these questions before the AP exam, check out UBQ, which is on nerdnotes.com. It's a question bank of free questions essentially that you can use. You can find those proportional analysis questions that I was mentioning earlier. But yeah, other than that, share it with your friends, and good luck on the AP exam. Alright, take care guys.